Swayam Prabha. Digital India. Educated India.
So this is a part 2 lecture where we continue with non-idealities of the operational amplifier. First, we will discuss finite bandwidth effect. Originally, when we talked about ideal operational amplifier, we assumed that the op-amp has infinite bandwidth, which means it can respond to any frequency. In this particular case, we will look at realistic operational amplifier and effect of finite op-amp bandwidth on the circuits that we create using the op-amps. The second part is slew rate limitation of the operational amplifier. The operational amplifier has, inside the operational amplifier, there are some capacitors which are used for compensation purpose, which I'm going to explain it to you in the future. However, these capacitors cannot be instantaneously charged. So the voltage across these capacitors cannot change instantaneously. And this results into limitation in terms of how fast the op-amp can respond to given input. And that is what we're going to discuss in the slew rate limitations of the op-amp. I would assume that you have had a chance to look at our tutorial on Bode plots. That would be very useful here. Okay, so the non-ideality we're going to study now is finite bandwidth. And when we say bandwidth, it's again small signal behavior of the amplifier. Okay. Now, when we talked about ideal amplifier, we said that it has, let's say, gain of 10,000, 1 million, something like that, right? And we said that it has infinite bandwidth, which means that any signal that you apply, any frequency, it will give you always the same gain. Now, in this particular case, just like Bode plots, I'm going to plot V out divided by Vi in dBs. That's your gain of the amplifier. Okay. And this would be your frequency in log scale. The log scale is important. Now, if the amplifier gain is A0 and if the bandwidth is infinite, then how would you plot it on this particular curve, in this particular chart? What you would see is it would look something like this. It would just go like that, and that would be 20 log of gain A0. This would be your ideal op-amp frequency response. But we all know that there will be some limitation. You're not going to get such a response. We will have some capacitive elements inside the op-amp, and that will cause this gain to drop, and we like to call that roll off. So you can model the open loop gain of the amplifier of op-amp as A0 ideally, or more realistically it would look like A0 divided by 1 plus S divided by P1. Here P1 represents first pole. What this is telling you is the following. We are assuming the op-amp to be a one pole system. It has only one pole and the pole is at P1. So when we do frequency domain analysis, we substitute S is equal to J omega. Okay. And you can quickly see that when your frequency is equal to the pole frequency, the mod of AV will look like A0 divided by square root of 1 plus omega divided by P1 square. That's the magnitude. And when omega is equal to P1 at the pole frequency, we will see this looks like A0 divided by root 2. And root 2 in the dB terms is 3 dB, minus 3 dB. Okay. Now this is something that you have looked at it from the body plot point of view. I'm just telling you that the OPAMP, we can assume for the sake of discussion, has only one pole for now, and the pole location is at P1, some frequency P1. So with pole location at frequency P1, the OPAMP response is going to look like this. Let's say this is where that pole location P1 is. The key thing to note here is we should make this as omega, which is 2 pi f. Otherwise, you have to bring in 2 pi everywhere. Okay. So if this is P1, then at this P1 location, we would expect the gain to drop by 3 dB. This is the 3 dB factor. And as we have seen in the body plot, what we would see is the following. We would see the gain drop right here, 3 dB, and then it will continue dropping like this. And this would be 0 dB on the y-axis. Okay. So you can quickly see at this particular frequency, the gain has dropped to unity gain because it's 0 dB. 0 dB means is equal to 1. That means AV is equal to 1. And this is called unity gain. And the frequency here we can call this as UGF, unity gain frequency. Okay. To keep things simple, I'm going to call this as FP1. FP1 is, we can say, omega is equal to 2 pi f. All right. So this is equal to 2 pi FP1. Just the scaling factor so that it becomes easy for us. Okay. And this is our frequency f. So this is f unity gain frequency, where the gain will drop to 1 or 0 dB. Now let's do a little more of analysis here. We're going to start off again with this particular expression, which is a one pole model of the OPAMP that we're going to use. So AV is equal to 1, mod of AV is equal to 1 at the unity gain frequency at f UGF unity gain frequency. So we can say that A0 divided by 1 plus S will be J 2 pi F UGF divided by 2 pi F P1. All I'm doing is I'm substituting in this particular equation. And this will be equal to, you can see it's A0 divided by mod of 1 plus, the 2 pi will go away, J times F UGF divided by F P1. Now, if you look at this particular expression, you can already see from the graph that FP1 is lot less than FUGF. Why? Because the gain is very high. If the gain is high of the OPAMP, then FP1 is going to be lot smaller than FUGF. So we can approximate here saying that this is equal to A0 divided by FUGF divided by FP1. Okay, and that tells us that brings back to one very important feature of a one pole system, and that is going to be, so 1 is equal to A0 divided by FUGF divided by FP1, which gives you FUGF is equal to FP1 times A0. What does this tell us? So this FP1 represents bandwidth of the amplifier. Bandwidth is the frequency where the gain drops by 3 dB. Bandwidth of the amplifier, and A0 represents DC gain of the amplifier. Okay, and FUGF is this frequency that is given. At that frequency the gain is equal to 1. Okay, so what this is telling you, that the gain bandwidth product of the amplifier is constant, and this is equal to FUGF. So FUGF is equal to of amplifier. Okay. So next we are going to go through one example which will clarify this business of gain bandwidth product. I already introduced the concept, but let's go through that and confirm whatever I am telling you. Okay. So I'm going to take an example of inverting amplifier. So this is the way it looks like: minus, plus, R2, R1. And we already know from the previous lectures that the gain, which is V out, and I made a mistake, small mistake here, let's erase that, V in. V out divided by V in is equal to minus R2 divided by R1. This would be the case if the op-amp is ideal with infinite gain, and if the op-amp has gain which is AV, we have already figured out that this term modifies to 1 plus R2 divided by R1 divided by 1 over AV. Okay. Now we already went through one pole approximation for the op-amp, where we said that, hey, we can model the open loop gain of the op-amp as a single pole response, where AV would look like A0. A0 is the DC gain when S is equal to 0, and as a function of frequency, AV is given by A0 divided by 1 plus, this is the terminology I'm talking about, 1 plus S divided by P1. P1 being the location of the first pole. Okay. So let's substitute AV is equal to A0 divided by 1 plus S divided by P1 in this particular expression, and let's see what happens, and you will see something interesting result that will come out of it. So gain G is given by minus R2 divided by R1 divided by 1 plus R2 divided by R1, and here we have A0 and 1 plus S divided by P1. Okay. So this term right here, I can split it in two pieces as 1 divided by A0 plus S divided by A0 P1. And then we can spread this expression out. Then it will look like this. This would look like minus R2 divided by R1 divided by 1 plus 1 divided by A0, 1 plus R2 divided by R1 plus I'm going to reformat this expression, just 1 minute. R1 times S divided by A0 P1. Okay. Now I'm going to say that, hey, the DC gain A0 is pretty large. So A0 is much greater than 1 plus R2 divided by R1. Okay. And then I can ignore this particular term first. And I'm going to rework this slightly, which you will see what that looks like. R2 divided by R1. I ignored the term in the red. This term I'm going to ignore. And you will get 1 plus S and then we will have A0 P1 divided by 1 plus R2 over R1. Okay. So we already looked at this term A0 P1. What is that called? Let me slowly go back to the previous case. A0 P1 is this particular intersection point which we looked here. I'm showing it in red now. So A0 P1 or FP1 is equal to the unity gain frequency. If this is F, then this is F. If this is omega, then the unity gain frequency part here will be also omega. Okay, that's just multiplication of 2 pi. So we can say here this is equal to minus R2 divided by R1 divided by 1 plus S divided by omega UGF divided by 1 plus R2 divided by R1. Okay. So compare this to our original one pole response. This also looks like a one pole response, except the pole location has been modified to omega UGF divided by 1 plus R2 by R1. So what does this really mean? This means that in our, let me redraw the characteristics one more time. So if we had ideal op-amp with gain of A0, then we expect this to be the frequency response, ideal op-amp. This is 20 log A, and this is your F log scale. And if we have first pole, which is FP1, then we say that From that point onwards, we will start dropping and the yellow characteristics happens. Something like this. And this is going to be our F unity gain frequency. And if we use the same op-amp in inverting gain configuration, then what you will see is, let's use different color, you will see this green curve, which looks something like this. Something like this will happen. And now this would be your 20 log R2 over R1, and the pole location has been modified to F UGF divided by 1 plus R2 divided by R1. Okay. Now we can do the exact same analysis for a non-inverting amplifier, where you have circuit that looks like this, and you apply input here, V in R2 over R1, and in this case the gain would look very similar. You will see 1 plus R2 divided by R1 divided by 1 plus S divided by omega UGF divided by 1 plus R2 divided by R1. Okay. So the difference being this, this one that shows up here because it's a non-inverting configuration. Okay. I would encourage you to go through this derivation on your own and convince yourself. Once again, just so that you don't get confused, omega is equal to 2 pi f, because I am using these terms interchangeably. Whenever we say omega, this is 2 pi f, so omega UGF is equal to 2 pi f UGF, and omega P1 for that matters is equal to 2 pi FP1. Okay, don't miss out this 2 pi factor. F is in hertz and omega is in radian per second, angular frequency. All right. Now we will move on to the next limitation of the operational amplifier. Next thing we're going to talk about is called slew rate of the operational amplifier. Now slew rate is a large signal behavior. I'm going to explain you all that. Just going to keep that in mind. Okay. What does slew rate mean? Slew rate means the rate of change I'll go over this again. Let's say we take an operational amplifier that looks like this. Okay, and then I connect it in a negative feedback mode like this, and I have V in here and this is V out. Okay, and for the sake of discussion, let's plot input and output. This is time and this is volts. Let's say the input changes in this fashion, which means I am applying a step signal at the input Vin. Now, if this amplifier was ideal and it had no limitations, then we expect the output to look exactly same as the input, except for the gain AV. The output should change exactly this way. Unfortunately, that's not the case. Op-amp has some kind of capacitive element in there, and as soon as you have any kind of capacitive element, then the voltage across the capacitor cannot change instantaneously. So there is maximum rate at which the output can change, and that's the slew rate limitation of the op-amp. So what I'm going to show you here is the rate at which the output of the op-amp can change is something like this, and this is the slew rate. So this is the actual V out, and this is the slew rate of the op-amp. Is the slope. So what decides this slew rate? Since we have not dug inside the op-amp yet, I'm just going to tell you that there is some capacitance somewhere, and there is some, because the op-amp has doesn't have infinite amount of current that it's going to take from the supply. It will have some limited amount of current. So the slew rate of the op-amp will be given by some maximum current that we can use to charge some capacitor inside the op-amp. We don't know any of these yet. Those we are going to study them later on as we go along and dig inside the op-amp. But for the sake of discussion right now, there is some maximum current Imax and some capacitance Cc inside the op-amp, which will limit our rate of change at the output to the slew rates. Okay, the unit of the slew rate is volts per microsecond. The reason we use microsecond is otherwise it will become megavolts per second, and that becomes a little bit impractical to deal with. So we use volts per microsecond. As I already said, this is a nonlinear effect. So slew rate is a nonlinear effect and large signal effect, large signal behavior of the op-amp. So you have to keep in mind when you are applying a large signal input to the op-amp. However, the slewing can also impact your small signal behavior. And I'm going to give you an example of that. Let's take this example of a unity gain feedback case itself. So example, let's take an op-amp, and that looks like this. Make sure that you observe the feedback part. The feedback has to be negative, otherwise you will not get the same answer. So V in, V out, okay, and you're given that the slew rate of the op-amp is 10 volts per microsecond. That's given to you. All right. Now let's say I apply V input. V input is equal to V peak sine omega t. Okay. Given that, let's say this is a sine wave that's going in, and we can figure out dV in. Derivative of this with respect to time would be sine omega t will give you derivative, that would be omega cos omega t times Vp. So the slew rate dV out by dt maximum, what would that be? That in this case it would be dV in by dt maximum, which would be equal to cos omega t. Maximum value is going to be 1, and that would happen at omega t equal to 0, 2 pi, pi, all those numbers, right? So this would look like Vp times omega, and then we can write this as Vp times 2 pi f. Now let's say I'm applying for a frequency signal of 10 megahertz and V peak is equal to 1 volt. Okay. So in this particular case, our desired dV out by dt is going to be equal to omega Vp, which is equal to 2 pi f times V peak. So let's substitute the values. So dV out by dt will be equal to 2 pi. Frequency is 10 megahertz, which is 10 to the power 10 6 multiplied by 1 volts. And what is that? Come out to be 20 pi volts per microseconds. Keep close attention to your units. Okay. And this is equal to 62.8 volts per microsecond. So you can already see this number is much larger than the slew rate of the op-amp, which is, we said, is 10 volts per microsecond. So what will happen if we use this op-amp and we give this input signal? So let's say we draw this again, plus minus, okay. So we are applying input voltage here, and this is our output voltage. So the input voltage looks like this. So the slope at these points is going to be 62.8 volts per microsecond. Unfortunately, our op-amp is slowing, so it cannot give you that kind of rate of change. So the op-amp output is going to look like this because it can only do 10 volts per second. So it will go something like this maybe, and it would start slowing back, and it will not even look linear. So that's why I said we are applying a large signal and we expect sine wave at the output. Unfortunately, the slew rate limitation of the op-amp, which will not give you the same behavior that you expected, and this is the slew rate. In this case, it's 10 volts per microsecond. Okay, so we have discussed so far various limitations or non-idealities of the op-amp. Now we are going to change our gears in a future lectures, and we are going to get inside. Now that we have covered the op-amp as a black box and made different circuits, we are going to go inside the op-amp. First, we will start with some devices like diodes, bipolar junction transistors, MOSFETs. We'll do some basics for that, and then we will start building different circuits using these components. Thank you.